connectivity and such kind of application. And by the end of the day, we hope that those officers from different agency can get a hand around this application and can create the training data, and eventually, hopefully, they can share the data with us to empower our algorithm in the backend. So with that background, I would like to go into another part of this presentation, which is more on the introduction of remote sensing. It's really difficult for me at the moment to talk about remote sensing and detail of remote sensing because I see so many experts already in the room, and there might be some people much more better than me and more experienced than me for this area, but I try to keep it as much as possible simple so that those people without remote sensing background also can get a hand around the material that we present today. So in general, in remote sensing, we have two different systems, right? One system is, we call it SAR system, or active system, or synthetic aperture radar system, and the other one is optical system. Now you may wonder that how these two systems are different. Well, in the case of optical system, hold the system together works very similar to our vision. In the presence of sunlight in the morning time, if the sky is clear, we can see all the objects close to us, and that's how our eyes work, by capturing the reflectance of sunlight from different objects. But there is an issue on that particular system. If you look into the left-hand side image, you see that since that system works exactly like our eyes, when you have obstacle on the surface or above the surface of the Earth, there is very difficult to get a clear image. And you see in the left picture that now that we have cloud presence, more than half of the pixel in the image are useless because you cannot get any information from the Earth's surface. That's actually a very major issue, especially in tropical region and Southeast Asian country, because mainly all over around the year we have this presence of the clouds, so we cannot get really good quality of the optical images. So to compensate that, scientists came with the idea of synthetic aperture radar system, which instead of relying on the sunlight or sun energy, we have a sensor which itself emits the radiation and capture its own radiation. And since that radiation can go through the cloud cover, regardless whether the sky is clear or not, we get some image from the Earth's surface. And that is actually one of the most important and most useful source of information that we have in Southeast Asia and tropical area. But as you can imagine from even from this image and last image, there is a very fundamental difference between optical images and SAR images. And SAR images in particular are not easy to understand the imagery. You need to have some certain level of expertise or experience to understand this SAR image. And that's count for one of the biggest disadvantage of this imagery. As you can see in the left-hand side, when we have the optical sensor imagery, it's very easy to visually interpret what feature we have on the ground. But on the right-hand side, when we have the SAR imagery, it's really difficult to interpret without expertise what we have on the Earth. And if I want to put it in a very simple phrase, what you can see through the optical imagery is about the vegetation, surface feature, and basically reflectance of the surface. But from the SAR perspective, what you can see is surface roughness. So you don't see the feature, but you see the roughness of the surface. And that's really important information for us to deal with later on. So the takeout comments from this slide would be SAR image are really useful, especially in the case of cloudy atmosphere and cloudy condition, but they also have this disadvantage of being difficult to be interpreted. So, excuse me. So now I want to dive a little bit more into the SAR information and SAR basically properties. Unlike sunlight, which has different wavelength from the visible infrared, and there is a wide range of wavelengths, SAR basically operate on the specific wavelength. Why? The reason that this is important is that basically with that specific wavelength, basically work like a special glass for eyes. When you put a special glass on your eyes, you could see specific objects and the other object would be transparent into your eyes. SAR system also work like that, depending on what wavelength of sensor you select. The information that you get from the Earth's surface would be really different. As a rule of thumb, if we want to elaborate a little bit about the impact of wavelength and what you see on the Earth, you can imagine that you can see on the Earth's surface any roughness that the size of roughness is bigger or at least equal to the wavelength of your SAR sensor. Anything smaller than that would be transparent. And that's why I said that SAR system usually work like a special glass on your eye, because you don't see anything else but what is designed you can see. So here on the right-hand side, I have a very good example from two different SAR sensors. One of them is C-band SAR, which has a around 6 centimeter wavelength, and it's based on Sentinel-1 imagery. And then we have the L-band SAR, which is wider and about 24 centimeter. And when you, if you look at the first example, which is rubber plantation, you see that with the C-band or short wavelength, it's almost difficult, almost impossible to differentiate different character in the rubber plantation. While if you use L-band with higher wavelength, you have this chance to penetrate, you have this chance that signal can penetrate into the canopy, interact with the canopy and return back with more information. That's why in the right-hand side, you see that now the rubber plantation, the situation of different rubber plantation are much more clear in the case of L-band. And the second example also is really good and related example, because that's related to inundated forest. And you can see that it's actually almost impossible to see or to realize the inundated floodplain forest using only C-band data, because C-band data get stuck into top of the canopy and there would be that. But L-band would have a chance to penetrate more into the detail, interact with the trunk of the tree, interact with the surface and the water beneath the tree, and come back with the more information. That's why in right-hand side picture, you get more information using the higher wavelength. So that was just to summarize what I talk on this slide or in this page. the comments that you can take with you on home is that the radar, basically you can see with the SAR system, you can see surface feature, which their size is basically bigger or at least equal to size of the your wavelength, and the higher the wavelength, more power to penetrate into the canopy of the trees and vegetation on the ground. Now, talking about SAR, we have, I thought that maybe it's good to look into how different feature or different surface roughness would look like into in these SAR imageries. So one of the feature, the reason that they look different is that they have different backscattering mechanism, different feature, different roughness. They would backscatter the signal in different way, and that's how we get to know what we have on the Earth. For example, in the first image, you see that if you look around that yellow circle, you see a very dark, basically line going from west to east. And that's actually a river or a water body. But the reason that you see this water body dark in this image is that you imagine that we have the water body here, and when the signal comes from the right angle, it hit the water body, but since the water body is really smooth and acts like a mirror, it would be backscatter in the different direction. So eventually what your sensor receives is very, very small portion of that original signal. So eventually you end up with the very small backscattering value and very dark pixel. That's how you realize that, okay, whatever we have on the ground has very smooth surface, like a usual case is a good example is water body. Then let's look to other example from the same area. You see the second circle, which is also dark, but not as dark as the first pixels or bunch of pixels that we had. So from here, I understand that, okay, whatever we have on the Earth's surface is basically showing a very small backscattering, but it's not as small as the previous one. So it means that your sensor is receiving back some portion of the signal, but it's not the full, and you have a very, very small backscattering value. And when we have such cases, this could be basically, for example, deforested area or agriculture land that just the machinery tilted till the area. So the surface roughness is a little bit high, but it still has the, it's not that much high. So it's equally diffuse all the incoming backscattering to different direction, and very small portion would go back to the sensor. And as a rule of thumb, if this surface roughness is, as the surface roughness increase, the backscattering also increase. So you get something brighter. The third example is another type of the backscattering mechanism. This is volume scattering. This is when you have some medium, some proxy that your incoming signal go through, interact with that, and then come back to the sensor. And it is usually happening in the forested area, and you see that this is almost Amazon basin, and you can see that the backscattering is a little bit high in compared to last two examples. And then we have another interesting backscattering mechanism, which we call it double bounce scattering. Sorry, I forgot to mention that the previous one, we call it volume backscattering because it comes from the volume and median. And medium, sorry. And then this example is basically I will try to turn on my laser pointer. So this example is basically a double bounce scattering. That happened when you have a very smooth surface, but you have another surface, again, smooth surface, perpendicularly placed to that surface. And what happened is that the signal comes and hit the surface, and from the surface hit the other object which is perpendicular to that, and then go back to the sensor. So the majority of incoming signal eventually end up to the sensor. So that's why we end up with very bright pixels, as you can see here in the this one is my laser pointer is a little bit slow, but you see the yellow circle at very right part of the image. Now, we see double bounce scattering usually in the case of urban area. You have a huge, the most contribution of the backscattering in urban area would be with the property of the double bounce. And then sometimes you have this double bounce in the case of flooded or inundated vegetation, like what we are going to talk today, mangrove forest. Again, in those inundated vegetation, we have the same mechanism of double bounce, meaning that the incoming signal hits the water beneath the vegetation, then interact with the trunk of the tree, and then go back to the sensor. So that's why you see the very white pixel again over there. With that background, I hope you could understand what kind of mechanism we have when we look into different pixel or different SAR images. I forgot to mention about this in the beginning, but all the material would be available to you, so you can get a hand on the material, but you can always refer to the resources that we put at the top of each page. You can get more detailed information from the original resource as well. So now that you have this image and you have this basic understanding of SAR system, how the backscattering mechanism, let me introduce ALOS-2 data. ALOS-2 is basically one of these SAR system, and ALOS stands for Advanced Land Observation Satellites 2, which is a mission now still operating since 2014. Run by Japanese Aerospace Exploration Agency, or JAXA. And this information, probably you know better than me that the L-band SAR is really informative, especially in the context of the forest application and inundated lands. They are really informative data, but those are not, the application of the ALOS-2 data originally is not designed only for those applications. These data originally designed for disaster monitoring and of the damaged area after disasters, also for the infrastructure assessment, and then agriculture and cultivation is another application of this data, and forestry, of course. And there are other applications that you see probably these data have been used, like ice detection or oil spill detection as well. So from now on, we mainly what we talk about is mainly on L-band SAR. We talk about a specific wavelength of SAR system, which is L-band, and L-band is about 25 centimeter. And from now on, we mainly work with this data. And before going through that, please let me go for a very brief overview of mangrove forest. It is really difficult for me to talk about a mangrove ecosystem because I know that BRIN And in specifically and in general, Indonesia has very, very good experts on the mangrove conservation. So it's really difficult for me to talk about that. But whatever I brought here is based on their, efforts. So I'm not really knowledgeable myself on the specifically on the mangrove. But as Dr. Arif also mentioned at the beginning of this session, mangrove ecosystem are one of the most important ecosystem that we have. They host a wide variety of biomass, the wide variety of inhabitants. You can see in the figure in the right-hand side that there is a diverse and wide range of inhabitants around this coastal area, which is the habitat of the mangrove. And specifically, if you look at the Indonesian coastline, you see that how this area are rich in terms of the biodiversity. So it is basically needless to mention that how this is important for us as a global community to save this part. And Arif-san also mentioned at the beginning that the carbon content of the mangrove forest, I also came across, I guess, the same paper that they are even higher than the Amazon rainforest. So mangrove forests also contribute into the carbon credits and climate change and global warming. But unfortunately, although there is too much benefits into this mangrove forest, but these mangrove forests have been a target for loss. And during past couple of decades, the extent of mangrove forest has been going down. But in the recent 10, 15 years, I believe it has been a very great effort. So the sloping of this degradation is kind of slowing down. But to monitor the situation of the mangrove forest, we need to have cost-effective methods. It's not really effective anymore, given for example, in the case of Indonesia, given the extent of the country, it's not efficient to go only with the survey and the field observation. We need to have some more cost-benefit approach. So remote sensing is always, satellite observation is always there for such kind of application. But one of the issue that, not one, but three main issue that we face usually when it comes to remote sensing and mangrove is that usually, as you know better than me, mangrove are located in the intertidal coastal line, and they have a narrow band, and we need to have high resolution imagery to observe them. Coarse imagery, usually they are not suitable for that kind of application. And also, again, this is Indonesia, this is tropical area, always covered with clouds. So we need to have something like a SAR system, which we don't have any problem or issue with the cloud cover. And the third problem is that since these mangrove are located in the intertidal zone, we always have this challenge of the dynamic ecosystem when the water level goes up and down. So given all these limitations, L-band SAR data and ALOS-2 data have been proving be very useful data for mangrove mapping. And there has been so many literature and research has been done with Indonesian researcher and also internationally on the application of L-band SAR and mangrove. And that information has been proved to be very useful and one of the best proxy to monitor the mangrove situation. So we talked about different backscattering mechanism and things like that in the previous section. But this time I would like to bring your attention more toward the mangrove and remote sensing and basically L-band remote sensing of the mangrove forest. If you look into the mangrove forest, you see that there are three main scattering mechanisms happening in the mangrove forest. The first one is single bounce or direct backscattering. The third one, which here is in the yellow color, I hope you can see. And then the second one would be volume scattering, showing with the white color, and then would be the double bounce scattering. But which one is the dominant and the main backscattering property for mangrove? It is something that it depends and it's depend on situation with your mangrove. By saying that, I mean, when you have the left-hand side figure, in left-hand side figure, when you have a little bit immature or young mangrove, the canopy is not that much closed. The canopy is a little bit open. And then the root system also is not that much complex. So you see different mechanism in compared to the mature one. As the mangrove grow more mature, you can see that the volume scattering decrease. And sorry, let me see. As the mangrove, as the mangrove is younger, you see that the volume, the double bounce scattering, which you see in the first image on the bottom of the slide, the double bounce scattering is high. And as we go through the mature phase, you see the less component of the double bounce scattering because the canopy are too dense and there is no direct interaction with the water body, and this root system also very dense. So what you see and which one of these backscattering mechanisms are dominant in the case of mangrove, it's really depend on what mangrove you are looking into. So there is no fixed rule that we can say that, okay, if your backscattering value is from this decibel to this decibel, probably you see this. So it's varied. But if you look and compare mangrove with other features, more specifically with forest, you would see some more or less same situation. If you look into the, the HH polarization usually has a component of double bounce scattering. And if you compare HH component in the rainforest and compare it with the mangrove forest, you see that for mangrove forest, we have a little bit lower decibel, a little bit lower backscattering on HH component. The reason is that the root system is so complex and there is not a very clear double bounce mechanism. And usually the HH or even VV in the Sentinel-2, you see a little bit lower backscattering. But in the case of HV, which we have more components of the volume scattering, again, you see a little bit lower decibel in compared to the rainforest. That's because, again, the canopy of the trees are too dense and the volume scattering also decrease as the mangroves goes older. And the last picture, probably you can see a more visible difference between forest area and mangrove. Those narrow belt around the coastal line that has been showing here by different color of circle, you see that those areas are mainly mangrove. Now, with that background on the remote sensing in general, SAR in a specific, and more specifically on the L-band SAR, I would like to move to another part of this presentation, which is more on the cloud-based. As I mentioned at the beginning, nowadays with the volume of the data, it's much more, it's getting day by day is much more difficult for the data provider to manage their data, to archive their data. And it's not only for them, it's also for us as a user, because handling the data in our servers, in our local PC, it's getting more difficult because the volume of the data is getting higher. You get the higher spatial resolution. So the volume is incredibly high. So to overcome with that, it has been a long time that the community is working with cloud systems, so that you can rely on a third-party resources for having your data, storing your data, and working on that. One of those cloud platform is Google Earth Engine, or in short, GE, which is a planetary scale platform specifically for the Earth observation data, and obviously managed by Google. And I'm quite sure that so many of you have been working for a long time with the Google Earth Engine, so that you know how extent the data archive is, that so many satellite imagery which are already publicly available, they are located into the Google Earth Engine archive, so you can easily access to that. But one, if you are not familiar with the, or if you are not particularly into the remote sensing community, you may wonder that why really these systems are important for us. I try to bring an example here in the left-hand side figure. Traditionally and conventionally, we had to take so many steps from data to information, and I'm quite sure that so many people already experience and know the hassle and the pain of this. If you want to work with satellite imagery, at the first step, you needed to access a data provider portal. For that, you needed to have the internet connection, and you needed to have a PC with the good connection. And then you needed to download the data. Again, that would be really impacted by the internet conditions, so on and so forth. After downloading the data, now you need to manage your data on your local server or your local machine, which was, again, with tons of gigabyte of the data, it's not the easy job to do. And then now imagine you have all the data on your machine and your computer. You need to go for some pre-processing step, which is really difficult in some cases because you might not be familiar with all type of different data. So you need to take some knowledge on that and then start with the pre-processing. Now that you have all your data pre-processed, you can start your analysis. And after that, you can publish your analysis in different formats. So it was, to me, experiencing such a thing, it was a whole project for itself. I mean, getting the data, managing the data, pre-processing the data, it would take lots of time. But with the new, not actually new that much, but with the cloud computing platform, so many steps already has been removed. One of the main steps is that you don't need to directly go to specific portal to get specific data. You don't need to go to USGS to get the Landsat. You don't need to go to JAXA portal to get the ALOS data. You can have them all in one single platform. And then you don't need to be really worried about storing the tons of data in time series, because you have already on those data on the cloud server, which is huge steps for us as the remote sensing expert. And in majority of the cases, I come with the example of the ALOS-2 later in a minute, that in majority of the cases, some data are already pre-processed and available for you. Again, you are one step ahead and you can more faster go toward the producing information and knowledge out of your data. So with that, Google Earth Engine also is such a platform that archives tons of the data, and it stores the data, so you don't need to download any data on your local machine. And for running different analysis, you don't still need to necessarily work with your own machine CPU. You can work with on the CPU of the Google server. So this is a huge steps in, this was a huge step in the remote sensing analysis. But the issue with such kind of platform, Amazon Web Services also same, Google Earth Engine also the same, you need to have some certain level of knowledge about the data, and more importantly about the some specific computer language, coding language. So it depends on the platform. It could be Python, it could be JavaScript, but you need to have some level. That really limits those population who wants to use their data, because not even in the remote sensing community, everybody knows about language, coding language. So that's really limit the application of the data and platform. But to bring the power of the data to the basically end user, for example, mangrove forestry's officer or forestry ministry, you don't, basically those officers don't need to work and deal with the code and deal with the data itself. They need to have the map. So why not put some interface, some cover on all those codes, and give them some specific range of information so that they can play around and they can get the information that they need out of it. That's where BRIN and JAXA are actually collaborating with each other to develop this web-based application. So in the back end of this application, you would have the ALOS-2 data, training data, machine learning algorithm working integrately. And on the surface, the end user doesn't need to know any of them. They just need to set some parameter and just run the data or prepare their training data on this. So speaking of the ALOS data and Google Earth Engine, I want to introduce the ALOS data on the Google Earth Engine archive. The data that we have at the moment available publicly available on the Google Earth Engine, also Amazon Web Service, TELUS, and other platforms. It's ScanSAR level 2.2 data. The spatial resolution of the data is about 25 meters. The revisit time, the temporal resolution usually is about 40 days, but in some cases, especially in Indonesia, we have more frequent, like 14 days, each 14 days we have one scene. And we have this archive available from 2014, August 4th, and the latest data that we have at the moment is the July 31st of this year. Usually we have 2 months of data latency to have JAXA to put the data on the Earth Engine archive. And you can see on the screen the extent of the data coverage. It extends definitely whole Indonesia and Southeast area countries, also part of Africa and South America region as well. Those are the regions which are really important for the application of SAR and L-band. One more thing that I would like to introduce here is that this data also is important because of the formats that we have here. The format is in accordance with the CEOS card4L format. This format is specifically designed to be readily machine readable format and readily available data to analyze. So there has been some pre-processing and some steps has been taken. So the data is almost ready to be used for majority of the applications, except land subsidence and INSAR analysis. This information also, I hope you can use it in the future. Again, because this is Google Earth Engine, probably to download the data on your local machine, you would need to have some level of understanding on the code. But we also generated another user interface. You can set different parameter, and after like the time of observation, the date of observation, so on and so forth. And then by running the program, you can automatically download the data on that specific area that you want. I already put the link to the application in the material on the top, and also there is a tutorial available for that. So if you needed to know the detail, you can go and check. And for those people who are, remote sensing experts who are familiar with the Earth Engine, this is open source software. So you have access to the code, so you can look into the code and improve it in the way that you want. That was a side information that I thought might be interesting for you. And then from now on, I would like to move to the part which is more on the introduction of the application. Using the QR code, maybe you can scan the QR code and get access to the link. If not QR code, you can use the link at the top. Clicking on that link, you can access to the web-based application. Depending on your machine and your internet connection, it might take some time to load, but be patient, it would come up. And this is the general user interface, very easy to understand, friendly to use, I believe. Basically, the back-end mechanism of this user interface is very simple. We have, by default, we have a bunch of training data in the back end, and using a random forest algorithm, we make two different maps of Mangrove extension. One for earlier period and the one for later period. And comparing based on pixel-based comparison, we get to know that which area has been which area is basically showing some change. This is very simple mechanism behind how the algorithm works. So to introducing the panel, you have the first user input is about the time. You need to give two periods. The first for before image and then for after image. Before image is the one which have earlier observation. After is the one which have later observation. The things that I want to emphasize here is that the format, how you write down the date here must be exactly as we have here. It should start with 4 digits of year, then hyphen, then 2 digits of months, and then 2 digits of day. So this is the format that at the moment the application reads, and you need to take care of that and always check if you follow the same format or not. After that, we have another user input, which is about the area of interest. We have two areas of interest. One is covering whole Indonesia, and the other one is to define your specific area of interest. Depending on which checkbox you check, you would end up with different result. If you check the whole country and whole country, you would end up with the whole country shapefile. If you check drawing your own region of interest, some drawing tools will be activated for you, and you can draw specific polygon shape around the area that you want to work with specifically. After that, we have another user input. You know that SAR has two types of information, ascending and descending. So it depends, and depending of whether your image is ascending or descending, the image would look like different. So that's why we put orbit path information here. So the user can select to either go with descending or ascending, or just keep it empty, so that the algorithm would take both images, ascending and descending. And the last parameter in the properties setting is the speckle filter. SAR images in general, they are really, I mean, they inherently noisy. It's like a salt and pepper noise. So sometimes for easy understanding, you may need to have some speckle filtering. And here we take a very simple speckle filtering algorithm on backend that I don't go through that. But in case that your time interval is too small and too narrow and short, I would suggest to use that. But if you are looking into months of data or years of the data, you don't probably need to turn on the speckle filter. And then we come to training data part. Basically, in this version of application, we have three ways to define the training data. The first one is to use the default training data that we already have in the backend of the algorithm. And the second one is prepare the training data within this application that I will show in a minute, or importing your training data. I will discuss each of these steps from now on. For the default training data, we already have it in the backend, so you don't need to be worried about. The training data basically was prepared based on global Mangrove Forest Watch version 3, and we took around more than 6,000 points from mangrove forest and non-mangrove forest to train the algorithm in year 2020 for different orbit paths. For different orbit paths for the same year. So I mean, it is not the best training data that you can get, but still there is something there that you can start working with. But of course, this is a place that we need the support of the mangrove community the most to prepare the best data that's possible. Then we come to the main feature of this algorithm, which is preparing your data set, training data set within this within this application. This is something that I guess it's very unique feature. So that without going to, for example, Google, Earth Pro, or looking to high resolution imagery in QGIS or so on and so forth, you can prepare the training data inside of this application, looking into the SAR data and optical data together. So once you check the prepare the training data here, what will happen is that two new widgets will be open for you on your screen, which will help you to collect the training data. And beside of that, optical imagery also will be added on your screen. So because it's difficult to understand SAR images, even for the SAR experts, so you need to have some visual reference to that. Exactly on the same same period that you define the at the beginning for your SAR data. Optical imagery, which is here, is Sentinel-2, will be also shown on your screen. So you can refer to that for taking the data. And then using the pinpoint or the polygon features, you can start to take samples. But the limitation with this application is that for now, you can only take 2 class and not more than that. And the first class, whichever is it, need to be a target class. So whatever pixel that you collect over there would be the main class. For example, in the case of Mangrove, the first class must be taken from mangrove forest, and the second class would be other, would be water body, would be bears or forest and things like that. And the point that I'm really happy about this application is that this application enables you to also download the data for yourself. This is really important, and this is we hope we can work with this with the end user agencies from the Mangrove, because with their extensive knowledge on the area, they can collect the data here, training data, and they can, if there is some chance, they can share that data with us or with the remote sensing experts, so they can bring that data into the back end and improve the algorithm. But anyway, if you click on the bottom at the end, when you finish with taking your data, you get a URL, and you can automatically download the data in KML format. And then you can open that KML format in the QGIS, ArcGIS, any GIS platform. And the last part would be importing the training data into your application. This is a little bit tricky because to import the data, you need to have Google Earth Engine account. To use that application, you don't need to have a Google Earth Engine account. But to import the data, you need to import your data in your personal asset. And after that, share that asset link to in the text box over there. And your data need to be in a specific format. The table here shows the format that we have for now for the data. So whatever training data you prepare in any size, you need to have some information about HH backscattering value, VV ratio, which is the ratio of HH over HV, and also orbit path. So this table suggests how you need to prepare your training data and then import. These are some figures showing the result. You see there is some red pixel already shown. Those are the places with higher chance of disturbing of mangrove extent within the given period. And on the very left bottom side of your screen, you would see some accuracy assessment information. That would be the number of training data, the number of testing data, kappa coefficient, and overall accuracy. You see those area, and this is the mangrove extent map. These are, the green one is the extent of mangrove, the red one is the change within the period. Of course, the accuracy of these data is still not good enough. That's why we really hope to work with BRIN and BRIN partners to improve the accuracy, not only for training data, but also working with BRIN expert to improve the back-end algorithm and information. That's why in the afternoon time, we would have 20 excellent experts here to work on the back end of the algorithm together. And with that, I would like to wrap up the presentation, but after finishing, I would also like to share my screen to show live how to work with the application, but to summarize and coming out from the presentation material, I would say that we have this publicly available web-based application so that we can encourage our end user to use satellite imagery to understand how satellite imagery are powerful. And by the end of the day, with sharing with that, we hope that we can have their support for our collaboration with BRIN to improve the accuracy of such kind of assessment, not only using the training data, but also improving the algorithm as well. And we will be working closely with the BRIN experts and scientists to improve the accuracy. And we hope that not in very soon, we come back with the upgrading the algorithm and web-based application. With that, I would like to just for a minute to stop my sharing, and I would like to go in my so can you see my basically screen?
Yes.
You can?
Yes, yes.
You are not in the Zoom. Just give me a second. I guess with this, everybody now should see the screen in the room and online as well. So this is the web-based application interface. You can run this application in other locations as well, except apart from Indonesia, but in that case, you need to prepare your own training data. So as I mentioned here on the right-hand side, the first feature you need to select is the date. And the date is in a specific format of the 4-digit year, 2-digit months and day. And then you have two different basically option to select the study area. You can either go with the whole country, or you can go with your own area of interest. For the first try, let's go with the whole country. For the orbit path, I would like to go with the descending. I don't check the speckle filter, but you can, after setting all those things, you can apply. And depending on your internet connection, it would take some time for you to see this map. The first one is the shapefile of Indonesia. The second one is ALOS-2 median composition within the given period for before observation. And the first image is median composition for after and you see the both imagery coming up on your screen. And now we move to the training data preparation. The easiest way is to use the default one and then start. You see that there would be some accuracy assessment window popping up. And then again, depending on your internet connection, so on and so forth, that would take some time. The map will be shown over there. So in this case, you can see that the training data is about 1,188 training data and about 500 something testing data. So still you need to improve. I mean, the data set needs to be improved. And these red pixel that now shows on the screen are the places which probably have experienced some sort of change. And turning on the other maps, you can see the distribution maps within both periods, and you can overlay that together. This is how you work with the basically default training data sets. But let's go for the basically preparing the data sets here. So I keep the time as it is, as a default one, and then I try to go somewhere and draw basically a random area. You can make this very precise, but obviously I go with the random rough one. And now you can see the area has been drawn. Both image will be shown again, and then I go for the preparation of the data sets here. And once I click that, you see a new widget showed on your screen. Apart from ALOS imagery, we have optical imagery as well for the same period. I turn off before imagery and mainly focus on after to take the training data. And you can zoom in to be precise. And now if you want to start and taking data, you can make a new layer from here. Once this is the sign next to the color is in the circle format, means it's okay and ready to be sampled. And you can use different feature to take a sample. I use pin here. The pin take 1 pixel beneath. Again, I would like to emphasize on the point that the first class needs to be the target class. So this is Mangrove. So this must the samples must be taken from the Mangrove. And once you are done with the first class, you go for the second class. Now you see that the first class already deactivated, the second class activated. You can go and take other classes. And once you are done, if it is what you really want, and this is all about your training data, you can get the download link. The link will be issued for you, and here you see that at the top, you can download the KML of your data as well. And once you finish with your data, you only need to start by pushing the start button. And you see a summary of your data from all the data that you've taken. 23 of those data has been used for training, and 9 has been used for testing. Obviously, it is too small given the area is too small training data, and it was just for the demonstrating purpose. But this is the overall of the application. For the importing the your own training data set, you need to have a Google Earth Engine account. Those who have the Google Earth Engine account, they already know that how they can, if you have Google Earth Engine account, you only need to prepare your data set somewhere else. and then bring the data inside the Google Earth Engine using asset. And then you can select the new shapefile, then select your shapefile here from your local machine. For example, I go with this shapefile. You need to bring all the shapefile formats and then upload. Once it's finished uploading, your task will be, now it's in a gray color. Once it's finished, it's in blue, and then you can refresh your asset. The data would be shown here. And then once your data is there, you can go on your data. You see a share button next to it. You can click on that. You need to make it available for public so that the application can access to the data. Once you checked this, done, and then you can go to your data detail. You copy and paste this table ID, and then you paste this here and then run. That's all about the importing the external training data. With that, I would like to finish the presentation here. I'm not sure, maybe here I can also show you the extent of the ALOS data on Google Earth Engine. This is a simple 2-line comment, but you write the comment at the top of your screen, and the data will, after running, the data will be shown here. So the purpose of this training or the session was not about Google Earth Engine and technicality. It was about more on the background and some information about the application. So with that, I would like to finish my presentation, and hope you can enjoy working with the application and all the resources available. With that, Joko-san, over to you.
Okay, thank you, Dr. Pugah. Very nice presentation. And I think we have homework now to study more about your application.
Joko-san, can you give us a second? I cannot hear you. I will. Now I probably can hear you.
Oh, okay. Okay, thank you for.
Can you say something?
Yes, thank you for your presentation. Very nice presentation.
Now I can. Oh, this is mute. Okay, now
okay.
I can hear. Yeah.
Okay.
Yeah.
Yes, thank you for your presentation. Very nice material actually. And now we have homework to learn more about your application, and maybe we can work together to improve your application in the future. Okay, just remain 5 minutes actually. Maybe we still have time for one question. If you have question, please you can use this opportunity. Maybe by raise hand, and then I can detect. Okay, okay, Mbak Maria ya, Miss Maria. Okay, okay, please. Okay, Mbak Maria, silakan kalau mau bertanya. Okay, silakan Mbak.
Is my voice clear?
Okay,
yes.
Okay, no problem.
Okay, thank you, Mr. Joko, for the opportunity. Thank you very much, Mrs. Vega, for the very good and clear presentation and explanation. I have a question today regarding to your explanation about SAR especially. And I'm a college student from Polytechnic Statistics SAS, and I'm a total beginner in the forensic science field. So my question today is, the SAR data have a polarization, and as to my knowledge, please correct me if I'm wrong, the different combination of polarization of the CEOS-ARD data will give us different information and sensitivity about a certain object. So I have a difficulty to understand which polarization should I use to get the information I want. For example, if I want to see the landslide or the mangrove, which polarization should I use to get the information that I have, or should I combine all the polarization like HH, HV, VH, VV, and the other? Thank you.
So thank you for your question. To answer to your question, it's really depend, to my knowledge, it's really depend on the application. What do you want to get out of what information you want to see? But as a general rule, basically HH and VV, in the case of Sentinel-1, they have more components of double bound scattering. So in case that you want to see for example, urban area, that might be more powerful source of information. When you have when you want to see something with higher double bound scattering, probably you can use that. But in the case of vegetation, and especially woody vegetation with the trunk, I would recommend to go on VH or HV or VH polarization, because you would have the volume scattering also inside. So it's really depend. But if you are not sure, I would recommend you to use all the polarization that you have and let the algorithm decide you which one can be the best. Yeah, I hope I could answer your question.
Okay, Mbak Maria, enough for you?
Okay, thank you very much.
Joko-san also is really experienced. I really feel not comfortable talking in front of him. So Joko-san also, if there is a comment.
Thank you very much.
You're welcome.
Okay, actually the time is over. But is it okay if we extend only 5 minutes? Maybe one question. One question more. Please raise your hand. Okay, it is enough. Okay, there is no question more. So I think thank you, Dr. Pega, for your presentation. I think this application is very useful for us. And then I agree with you. We can collaboration more to improve your application. So I think we have collaboration with JAXA and BRIN. Then we can use this scheme. Okay. So I will give a conclusion today. Now we have application to monitor the change detection of mangrove developed by Dr. Pega. So we continue our collaboration. I think this application is very nice because Indonesia also has very wide mangrove area. Then we can try to monitor and detect mangrove in Indonesia. And then also now we have ALOS-2 data in Google Earth Engine. Actually, this is very special issue because previously may be very difficult to get ALOS-2 data from JAXA. Okay, once again, thank you, Dr. Pega, for joining us today. We hope that we can continue our collaboration, or maybe if possible we can make special training again related to this topic. I think many participants here, because we have more than 100 participants today, interest to study more about this. Okay, thank you. See you for the next BRINder program in the next session. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very
Have
much.
a good day. Thank you.
Thank
Thank you so much.
you.